Hello, everyone. We are honored to have today with us Igor Pak. I don't know if the camera can see him now.
Yes.
Okay. Igor is from UCLA. Before that, he was also a professor in University of Minnesota Twin Cities and MIT. I guess you can say the heart of his research is algebraic and enumerative combinatorics, but he does a surprisingly wide variety of topics, works in a surprising variety of topics. What else? He is also known for his blog, full of strong students, and all sorts of other things. Looking forward to hearing your talk today.
Thanks, Adam. Thank you so much. This was a surprisingly long introduction. So a pleasure to be here. I'll tell you what we did. I'll tell you problems that we started working on maybe 6 years ago and solved during COVID. So it's one of those COVID problems that we managed to solve. So the title is Domes over Curves. And I'll tell you what all those words mean, and so start with the definition. So by curve, I'm going to think of a curve as some kind of polygonal curve in a string, comprised of unit intervals. So it's exactly what you think it is. So we have, for example, that is some kind of curve, and all those intervals are unit intervals. Okay, so I'm going to think of all the closed curves. Closed curve, so it's a closed curve analysis. Okay. Everyone good with that? All right. So now, next definition, dome. Dome is
But that polygon doesn't have to lie in a plane.
no, it's not true. A dome is a polyhedral surface. And I'll just write field surface. Comprised of unit equilateral triangles. Okay, is this clear? So just an example would be the surface of a tetrahedron, of a unit tetrahedron. That's a dome. So the dome can have a boundary. So for example, this tetrahedron without a triangle at the bottom, that's still a dome. Okay, and the question is, so the boundary would be a curve. Well, so typically people would write the integral curve. And the question is, so the question that Kenyon asked is it true that every curve is a boundary of some dome? Okay, and I think that the question by Kenyon is every curve of integral curve boundary of a dome. And that's what I'll talk about. Okay, is the question clear? So let's do some examples. So let's start with a square. So the square obviously is the boundary of a dome because you can just pick on top of that sort of a top part of the heater. Okay. I don't know how to draw that, but that looks that way. Okay. Everyone good with it? All right. So the next one would be regular pentagon. You can do the same. Okay. Regular hexagon. That's even easier. You're done. You can just tile it with triangle. And now you get to 7 gone. 7 gone, and that's a little harder to draw. Yeah, here we go. Can you do it that way? Is that a boundary? Yes, no? No?
Well, if you put like an upside down triangle between two like triangles. You can't do the same trick because the lowest angle you can make is 52, and then it's just going to get smaller.
So if you start doing it this way, you're not going to reach the middle. So what do you do? It's true, but it's not easy. And one thing, so you can do it, but first of all, the surface is going to be, you can make an immersed, which means you can make a self-intersecting surface kind of like this, comprised of unit triangles, but that's very hard to visualize. I'm not going to draw that for you. It's going to have a lot of triangles. Go ahead.
So do the curves have to have like the same angles between?
No, I'll do more examples in a minute. So this is difficult, but on the other hand, as soon as you let's try a regular octagon. Can you do a regular octagon? I should say yes. That's because this one is suddenly easier. That's because you can. This is not pretty picture, but you can put a. Let's just pretend there is a square in it, and what you do is you can take the square and raise it a little bit. And when you raise it, you can make sure that that you have squares and triangles, equilateral triangles. But that's not enough. You need to have all the triangles. But you already know how to deal with the squares. Okay. And the same will work with the 10 gone, with the 12 gone even, and that's it. And all the easy polygons are done. Everything else is going to be hard. And that's where we work. That's where the work starts. So the answer to the question is both yes and no. And so the theorem 1. So I'll tell you both theorems, and then I'll explain what's going on. So theorem 1 says basically yes, there exist curves which have no domes. And in fact, I'll tell you precisely what it is. So if you take a row in our, I'll make. Let me do a definition first. I'll say row of AB in R3. That's a unit rhombus with diagonals A and B. Greater than 0. Okay. So for example, you can sort of look kind of like that. This is an R3. Okay. And then one theorem I can do, theorem one, rho, I don't know, let's say 1/pi has no dome. So that particular rhombus is not on the boundary of anything. And you can put here any small enough transcendental number if it's the same. Okay, so you can, and in fact, you can put here like 7 or something, like 19. That's still good. Say it again. This is an R3. So that the rhombus looks sort of like comprised of 4 sticks, which sort of look like that. I'm saying you cannot have two remaining diagonals to both transcendental and in the same way. They can be algebraically independent. So if you have a row of 1 over, well, let me not write more. So I can do more than that. I can prove it for some other for some other diagonals, but that's good enough. I think. Yeah.
What does A and E represent?
What
Diagonals of the rhombus?
Yeah.
Oh, the
A
A?
and
Oh,
of diagonal lines. So that's theorem 1. Theorem 2. Integral curves, which can be done are dense in the space of all curves, all integral curves. So to put it differently, if you have some kind of curve, and then you can perturb the vertices tiny little bit, and then you can do it. Okay.
So if the curves were right angles, you can handle that case.
I don't know what you're talking about.
yeah, because you
So-
can make them all squares. And that would work.
It's the angle between consecutive edges, not in a plane, in 3 space. Yeah. No,
You presumably you can just fill them with squares and then squares. You can fill with the top of octahedron. You can be done. Yeah, not the most interesting family of curves from that point of view. Okay. So the proofs of these two theorems, as you can imagine, are very, very different. Do you want to say it loud? No. Or you're just complaining? Yeah, I'm generally complaining. Okay. Oh, well, for people on Zoom, Boris just admitted he's generally complaining. So what I'm going to do is basically talk mostly about that, because that's a positive result, and I'll say maybe a tiny little bit about that. That is a difficult result. Okay. So this is kind of joke positive output. That result is essentially algebraic and uses tiny little bit of, well, it uses a little bit of topology, but topological. So what I'm going to do is tell you how to roughly approach this one. Okay. And it's actually kind of interesting. So some of the tools I'm gonna explain are gonna be interesting, regardless of anything else I say. And maybe. So let me start with the tools. So I think that's a beautiful thing. Do you know what the Stanis lemma? If you even if you forget anything else, I'm gonna say that's a beautiful question. So suppose you have U1 up to UN are let's say unit vectors in RT. So that the fixed unit vectors. Now what you can do is for every permutation sigma, you can write a sequence of points 0, U sigma of 1, U sigma of 1 plus U sigma of 2, dot, and then at the end, you're going to get sigma of 1 plus U sigma of 2 plus dot. So you basically, for every permutation, you're adding success, the vector successive. Okay, let me draw a picture in the following way. So those are some kind of unit vectors, and I should have said that U1 plus dot plus UN equal to 0. And now we're looking at so let's say you start with 0. This is U1, U2, U3, and so forth. So here's what you want. You want to measure the maximal distance from the origin to all of those points. Okay. So for every so denote by I don't know, B of sigma, maximal distance to this capital B of sigma. Okay, from the origin. And so we're looking at distances like that. I have only one color, I think. Or maybe I do have more colors. No, it's one color. So I can make a dotted line. Okay, so now the question is, can you always make this maximal small by doing permutations? So we're going to define for a set of vectors, we're going to define some kind of beta to be a minimum over all permutation sigma in a sum, B of sigma. And now comes a beautiful theorem of for every B, there exists some kind of number, let's call it K sub D, such that for every U1 up to UD as above, beta, which is really defined as, so this is set U, beta of U is going to be less than KD. Okay, so what I'm saying is that there is a universal constant which is independent on M. That's very important.
Well, that's the key point. Where,
Yeah,
but then the key point is independent of N.
yeah. But then you, from U1 to U1 up to, sorry, U1 up to Gen. So for every D, there exists KD such that for every N. Yeah,
Yeah, it wasn't for all.
I agree. Otherwise, it would be, I agree.
That makes it shy.
And in fact, so that is the Steinitz lemma, which, and in fact, it's more general than that. It's for every norm. It's even more general than that, but it's not super important. So this was about 100 years ago when he proved it, and in our paper, I should have written everything I'm saying is joined with Alexei Glazeri. So in our paper, we do a bit of a review what's going on. But the idea, Steinitz idea was very simple. So suppose, so somehow you want to generalize, I forgot whatever it's called, Weierstrass theorem, that when you have a series that's converging, but not absolutely converging, then you can rearrange you can rearrange the terms in the sum. When you have an infinite sum, you can rearrange the terms so that it can converge to anything you want. Okay, that's sort of standard result, easy to prove in high school. And Steinitz wanted to do that kind of stuff, and this was his way of approaching the problem, generalizing that in his way. Any of you seen this before? Okay, well, good. So in fact, the curious thing about the whole business is not much is known. So the constant K2 is known. That is the optimal constant is square root of 5/4. This is optimal. So that's what Steinitz somebody proved it later. Again, over 100 years ago, long time ago. And the K3 is not known already. Would be a nice project actually to figure that out. That is all. Shouldn't be that hard. So to understand that constant, we need an example of the following kind. So take one vector to the right. So k unit vector this way, k unit vector that way. No matter how rearrange the term, so and then standing k to infinity, then basically this is 1, this is 1/2. So this is 1/2. So that's where 5/4 comes from. From that example. In the limit. Okay. And what happens in R3 is not known. Okay. So when I understood this is related, I'll explain why it is related. When I understood this is related, I thought the problem is easy, and it was. So let me continue. The proof idea of theorem 2. Now the problem. So imagine you have some kind of curve. The idea would be to break it into two curves. Each of them is smaller, and then eventually you solve the problem for a quadrilateral. For quadrilateral, everything is equal. Okay. And this would work if, unfortunately, there's a tiny technical detail. The tiny technical detail is that this approach works if there is if those 2 points are not too far apart so that you can add a point of unit length in between them. Okay. Otherwise, things just don't work out technically. And now the idea is that you need to do something about your set of vectors to make them have distances which are not far apart. Okay. So let me tell you what exactly is going on and what do we do? Well, let's start with somehow suppose you have a tetrahedron. So everything is unit except for this edge, which is say alpha. Okay. Now, what is the boundary? The boundary consists of 4 edges. However, you can take that tetrahedron and attach the same one on the side. Then you can attach another one on the side. So you basically keep attaching the same kind of tetrahedron, and you can do it so that the boundary is going to be dense in the set of all boundaries with this diagonal alpha being fixed. You see? So in particular, you can make it almost flat. You can make it just almost exactly flat by if alpha is sort of arbitrary, so that the set of this tetrahedron that you attach is going to be dense. Now, that's the trick we're going to do to simplify the curve. So we're going to start with a large complicated curve, and we're gonna take let's say it consists of those 2 intervals, and we're gonna attach we're gonna take those 2 unit intervals and we're gonna make them lower them down by using this trick. Yeah.
Is the dome able to like pass through itself?
Yeah. Otherwise, I have nothing to say. Otherwise, everything is super difficult. Yeah, self-intersect. So what I'm going to do is I'm going to keep making everything very sort of. I'm going to start with the topmost point, and then I'm going to go with the next topmost point, and so forth. And I can do it from the other direction. And when I do it at the end, I'm going to get a curve which is almost flat. Okay, very, very close to the flat using this trick. Now, when I get it very, very close to the flat, I'm going to do another trick. So when I have, imagine, let me make a more complicated curve. So suppose, maybe not that complicated. So suppose this is my curve. What I can do is I can exchange this. So I have a. So I can create this. This is a unit distance. This is a unit distance. I can almost completely flip my rhombus to go in the opposite direction. You see? What this does is, if you think of that curve as being oriented, what this does is changes the order in which you're adding those 2 unit vectors. That makes a transposition. You see? If you can transpose any 2 vectors next to each other, you can make any transposition you want. Okay, and in particular, you can make sure that the maximal distance between any 2 points is very small. And so I'm not going to use Stein's lemma in dimension 3. I'm going to use it in dimension 2 when I know the bound, the square root of 5/4. And so at the end, I'm going to get some hugely self-intersecting curve, which is going to look like that. So there's a lot of triangles are sort of wrapped around here, everywhere. You don't see them; they're hugely self-intersecting, but that's what you get. And now it's sort of hard to visualize that, so that's why we're back to this picture. So if a curve is a quadrilateral, we're almost done. We know that. We already know that if it's a rhombi, I can get almost the same rhombi by using this trick. If the curve is a pentagon of some kind, doesn't have to be regular pentagon. It can sort of look. The pentagon can sort of look like that. I know that there's a way for me to draw. No, that's not. That's gonna be nicer. So I'm gonna take some triangle, start at this edge, and I'm gonna rotate it until this point is gonna be a distance at exactly 1 from that point. And by continuity, I should be able to do that. That will break everything into one equilateral triangle and 2 rhombi. 3-dimensional rhombi. So I can do it with a pentagon, and when it's a more complicated curve, so some kind of how many is it? 1, 2, 3, 4, 5, 6. Some kind of hexagon. I'm gonna do it the same way by splitting into 2 smaller curves. Now, yeah, so that is like. So the real argument sort of work backwards. You need to show that every curve can be approximated with some curves. So you need to ensure that all this construction actually does what you want to do. So there's a little bit of an issue with the order of 25, but that everything here is discrete, combinatorial, can be completely handled, and that is how a proof theorem too. That essentially the abstractions are not geometric. There is no issue with geometry. Almost every curve, in some sense. So for every curve, there's another curve very, very close to that one, which can be done. Okay, that's the first part. Is this okay? Any questions?
So where did you get this constant is small or?
So I used it right here. If the or right here to be precise, if the distance was very large, you wouldn't be able to do it. You can't cut it, and you can't cut it. This type of argument is not going to work. Those points are too far apart. So you need everything. You need the curve to be to affect a very small distance to be able to proceed with induction. It's a technical point, but that is the main point of the proof.
Maybe we just say that if there are any questions on Zoom, you're also welcome to ask.
How come we were able to use a constant for 2 dimensions if the problem is in 3 dimensions?
Because we made everything to be very, very close to the dimension, and we can control that. So
I think there is a question. Can we hear it?
Joe, do you want to ask a question?
Yes, How many triangles do you end up in the dome as a function of the number of unit segments in the curve?
Let me repeat the question. How many triangles do you end up with as a function of the number of segments in the curve? There is no function.
No, because that is actually, well, theoretically, maybe there is a function, but that, first of all, we don't compute it. Second of all, it depends on the number theoretic properties of those constants like alpha. And there are ways to bound that as well. But the answers are going to be huge and depend on depend on how close how well is the distribution of those points. Yeah, it's huge. We're not going to compute it, and it's going to be unbelievably large. So I think the answer is we don't do that, and I don't recommend anyone doing it.
So, how does this prove theorem two? That you could wiggle it a little bit to make it right?
Yeah. So at the end of the day, so imagine you have some kind of curve, and I'm starting with something that's in the plane or whatever, and I'm aiming to something very, very close. So I'm saying that there are some integers which count the number of times I do this trick around. When I'm gonna change alpha slightly, those angles are gonna change very slightly. Yeah, for every fixed constant, but they're gonna, if the constant is very large, it's gonna change very rapidly. But for every fixed constant, there is some bound depending on epsilon, which is gonna be my target, and I'm gonna use it over and over and over. It's gonna be some kind of giant power of how many triangles I'm gonna use, but at the end of the day, I can make sure that it lands almost exactly to the curve that you want. Any more questions about this?
Yeah, I have another question. This is Joe O'Rourke. If
Yeah, go ahead.
suppose you change the definition of a dome to be embedded rather than immersed.
Okay, so the question is, suppose domes are embedded rather than immersed. The answer is, I don't know what's going to happen, but I wouldn't know even if 7 Gond has an embedded dome. I don't know how to answer basic questions. That's not what I do. So presumably, for some curves, everything is going to become easy, because you can then have a knotted curve, which obviously is not going to have a dome. So the original Canaan's question is going to be super easy. But that's, again, I think it's a lesson in life. You shouldn't always go for the easiest thing. Try harder problems. So no, we don't do embedded curves, embedded dome. So I want to say a little bit about negative results. Because after all, essentially, when we told the Kenyan that the answer is negative, he was in a mild state of shock. He basically wasn't sure if that's even something we can, people can believe. That's not what the intuition tells you. And I'm not going to be able to prove that, but I'll tell you a couple of words that are relevant. So this is so for theorem 1, we use something called the theory of spaces. So spaces are certain type of valuations, and I'm not sure I want to explain exactly what they are. It's a rather old idea. But let me explain in a sort of basic language what's going on. What's going on is that imagine you have some kind of dome, and it's attached to well, let's make it slightly more plausible. It's attached to a quadrilateral. Okay. Now let's take the same dome and reflect it and attach to the quadrilateral on the other side. So it's gonna sort of look like that. Okay. And so here is a question. Can you make the whole construction to be flexible so that the dome sort of can breathe? Or is it always rigid? So just because you have a belt around the point where these two domes are attached to each other. So we believe no. We believe that's impossible. We cannot prove that. But the tools that would be needed in order to prove that, we know the tools. And those are the tools, which are sort of standard in rigidity theory. So essentially, the idea is the following. Imagine your dome is deforming. When dome is deforming, that means some diagonals are increasing and decreasing in size. You see? And so this diagonal may be increasing. That diagonal is so other diagonals are fixed, and some diagonals are fixed, and some diagonals are changing. Okay. Now, what happens is that what people in rigidity understand is that some diagonals have to be always algebraic, because they have to be, because of the combinatorial structure of the dome. They imagine those lengths are actually fixed, not one but any fixed numbers. Okay, those the length of those diagonals are going to be even if they're one, there are other diagonals which are still fixed, and we don't know what they are. They're some kind of variables, and those diagonals which change. There are certain diagonals which are solutions of algebraic polynomials in the length of all those numbers. Okay, that may seem a little strange. Why would that be true? But if you think about it, something is obviously going to be true. So imagine you have this kind of pentagonal cone. Okay, what is the degree of freedom of that pentagonal cone? Well, you can bend it here, right? And you can say bend it a little there, but that's it. There are only degree 2. On the other hand, there are 5 diagonals here. So if you have only 2 degrees of freedom and 5 diagonals like that, some of these diagonals are going to be expressible as algebraic polynomials in the other. That is the idea. Now, what the theory of spaces allows you to do is express the whole thing algebraic, and essentially sort of ignore the issue what is the precise algebraic relationship is between the diagonals, and just describe whether there exists a relationship or not between these diagonals. That's what it allows you to do. So what we can do is essentially we look at the whole realization space. So if the boundary is a rhombus, we can look at the whole realization space of this polyhedral surface, and we can say that, look, there are certain restrictions on the diagonals of this rhombus that we can have. in particular, you cannot have them both to be transcendental and algebraically independent of each other. Okay, on the other hand, if you have two numbers which are transcendental, algebraically independent of each other, because that means that they're not algebraic in all these ones which are unit distances of the triangles. So that it would mean that there are 2 degrees of freedom for this giant structure to work. So we cannot show that it's always rigid, but we can show that there is at most 1 degree of freedom. That's what we can prove, and that shows that not every rhombus can be domed, and that answers original Kenya's question. So that is my high level from point of view of what does this prove do. So the technical issues are many. The algebra is actually quite easy to set up. It precedes us. It goes back to. So for those of you who know, imagine you have a flexile polyhedron. There is a famous theorem due to Sabitas that the volume of that polyhedron is invariant under the flexon. So if you want to read a nice readable version of that, you can download my book and read it there. And along with the theory of spaces, which you need in order to understand that. So essentially, the algebra is easy, but there is a little bit of problem with the way the induction has to be structured in order to deal with all kinds of possible topologies the domes can have. If the domes are easier than the induction is easier, so the dome that is the induction is easier, but you still need to do. There is still some issue. And so somehow the issues are more topological than algebraic. Algebraic setup sort of precedes us, but it's never been applied to those type of questions. And I think that's all I wanted to say.
Thank you.